And let's see now what happens when the object speeds up, for example. Velocity changes. The displacement that is happening every second changes. So the first second, my object did a meter, and then it did another 3, and then it did another 5, and so forth. So I see it going from here to here, and then there, and then there. I see that it speeds up. I can tell it does a bigger distance every second. Okay, that means that velocity increases too. So initially the velocity was small, but then it became bigger, and then it became bigger. Velocity increases. Now, if we find the velocity in this case, we can see that the velocity increases by 2 every second. Okay, going to the position time graph, our graph will be like this in this case. The slope increases, velocity increases, we can see that. Now, it increases, and it increases at a constant rate. Okay, how much is this rate? We can find it by finding the slope again. So the slope in this graph, rise over run, the slope in this case is the rise, the increase in velocity, which is 6 minus 4 meters per second. Well, the change is 3 minus 2 seconds, which gives me a 2 divided by 1, 2 meters per second squared. So I see that my velocity changes by 2. Well, I knew that, but let's say I didn't know the graph, right? My velocity changes by 2 meters per second, meaning meters per second squared. So we decided to give the name of acceleration, use the symbol A, to be able to recognize and talk about the change in velocity. So the acceleration, which is the change in velocity, and it is the graph, it is the slope in the velocity time graph that shows us how velocity increases. So in this case, acceleration will be 2 meters per second squared. Now someone can tell me, all right, how did you find these values? How did you find that position changed like that? Let's say that I started by giving them and finding, but what if I didn't know them? How could I find them? Well, we can go back to the velocity time graph and find the area under the graph. The area under the graph, let's say for the first second, is this one. It's a triangle, so it's half base times height. So half the base is 1 second. The height is 2 meters per second, which gives me 1 meter. So the distance traveled in the first second is 1 meter. Going to the next, if I do the first 2 seconds, this triangle instead, I would need to do half. The base now is 2 seconds. And the height now is 4 meters per second, which gives me 4 meters. I found it. Okay, 4 meters is the displacement from the initial position for the first 2 seconds. Now, if I wanted to find the displacement from the initial position for the first 3 seconds, I would need to find the area of the big triangle. And that would be half base 3 seconds times the height which is 6 meters per second, which gives me 9 meters. That's it. So by finding the area under the graph, I can find the displacement from the previous position for that amount of time. So to review, the velocity time graph gives us a lot of information. It doesn't only give us the velocity, the instant velocity at any time. It gives us the rate of change, which is the acceleration, and it can give us the displacement traveled from the area under the graph. Now I want to show you something. Yeah, I'm laughing. So let's say, we saw that the distance traveled, the displacement traveled the first second was 1 meter. This area under the graph was 1 meter. And we did find that the displacement traveled the first 2 seconds was 4. Okay, so we see that as time doubles, the displacement does not double. It becomes 4 times bigger. Is this by accident? Can this happen in all cases? Yes. I want to show you something. I want to remind you something in geometry. So what do you have here? You have 2 triangles. This triangle, the area of this triangle, and the area of a triangle that is exactly double. You already know that the area of a shape that is exactly double, the area is 2 squared, meaning 4 times bigger. The area of a shape that is 3 times bigger is 3 squared times bigger. So when let me repeat. So when the shape is double, it's like the sizes are double, the area is 2 squared, meaning 4 times bigger. When the shape, all distances, all sides are 3 times bigger, the area becomes 3 squared, 9 times bigger, right? And we can see that. So the blue triangle that has double base, double height, and apparently the third side is also double, its area is 4 times bigger. And which means that I can show it with one more way. If I split, I'm trying to decide of the color. So if I split the blue triangle, I can see that by drawing this line, this triangle is exactly the same with this. And by drawing this line, I create 2 more. All these 4 triangles are equal, meaning that the initial includes 4 times the orange triangle. So it's 4 times bigger. The same can happen with the triangle that is 3 times bigger. I can split it. I don't know what color to use. So right now this triangle, the big one, has 1, 2, 3, 4, 5, 6, 7, 8, 9 triangles like this. So it's 9 times bigger. This is something that you can see very often in problems, and visualizing how this works can help you find the answer easier without needing to do any math. So we use that a lot, and I would like you to remember that. Now this is an acceleration time graph. Okay, so in our case, acceleration is constant. It's 2 meters squared meters per second squared the whole time. In this case, the slope doesn't have a meaning, but the area does. What is the area under the graph? This area, for example. How much is that area? It's base times height, so the area is 1 second times 2 meters per second squared. Getting rid of the square with a second, we find 2 meters per second. What you will see is that what we found is the change in velocity at that second, at the first second. So my velocity changed by 2. You can see that, so this is the change in velocity. If I find this area, I will find the change in velocity for this second, which is another 2 meters per second, meaning that the second my velocity changed by another 2. And of course, you do understand that it's exactly the same, right? So by finding the areas, I can find the change in velocity at that amount of time. So let's do a review. Let me try again. Right, so a position time graph can give us two informations. It can give us three. It can give us the position at every second, at every instant. It can give us the displacement between two times. Sorry. So after a small interruption, let's go back. So when we have a position time graph, we get three kinds of information. We can know the position at any second, therefore we can find the displacement between two positions. And through the slope, we can find the velocity. The slope gives us the velocity. Now, from the velocity time graph, we have even more. We can learn even more. From the velocity time graph, again, we can find the velocity at every instant. We can find how the change in velocity between two instants. From its slope, let's have a different color. From its slope, I can find the acceleration. And from the area underneath the graph, I can find the displacement. The acceleration time graph gives us the acceleration. In our cases, acceleration will be constant. Physics AP1, the acceleration is constant. The only case we see questions where acceleration changes will have nothing to do with finding how much acceleration changes or finding the velocity or the position after that. It will be a simple example like, I don't know, when acceleration changes, force changes. I don't know, something like that. All right. Now, from the area under the graph, the acceleration time graph, from the area, we can find the change in velocity. What you're going to see is that in most of the times, the graphs we have are velocity time graphs because they have everything. They can give us information about how position changes. They can give us information about the acceleration. They give everything.